Welcome again to the Rocking Reservoir Waves on Rock Physics-driven Machine Learning series. In this third episode, we'll hear and learn more from reservoir expert Jyoti Malik, the intricacies of this integrated rock physics-driven machine learning workflow, and explore more details about convolutional neural networks and their applications. To recap, if you missed our first two episodes, we explored the world of machine learning and its application in the energy sector, specifically focusing on reservoir characterization and the challenges posed by limited well data. The solution offered was using rock physics model to build a synthetic catalog and then using convolutional neural networks to estimate reservoir properties. Thank you, Jyoti, for joining us today.
Thank you, Ayan, for having me again.
Jyoti, during our last conversation, you shared the details about rock physics-guided machine learning and your experience. Now, could you elaborate further on the convolutional neural networks?
Yes, Ayan. Convolutional neural networks are widely used for image classification. And in order to extract main features from an image and to reduce overall dimension for fast computation, the network's architecture consists of a series of convolution and pooling layers. After several iterations, the output is flattened into a vector. This flattened layer is used as input to a fully connected neural network, which can output class predictions using softmax, or in our deployment, a continuous variable. Now, if I connect this with the kind of image we are using in reservoir characterization, then we have seismic gathered data as images. During convolutional neural network operator training, the seismic gather goes through a series of convolution and pooling, and the output is a flattened layer. This flattened layer is now further used in a neural network with several hidden layers and finally predicting various reservoir properties using one network.
Thank you, Jyoti, for explaining the CNN in detail. I am now curious about the training process. Do you exclusively use synthetic catalog, or is real seismic data also part of the training?
That's a very insightful question, Ayn. And in fact, this is also one of the key highlights as how we have implemented CNN in Hampson-Russell. Initially, we start training CNN using synthetic dataset. However, after building the CNN operator, we bring real seismic gather to further improve our training. And this is what we call transfer learning. Mathematically, what we are doing is that after we train using synthetic data, we freeze the convolutional layers and then update the weights in deep neural network using real seismic data. So indeed, we get a validation very much during the CNN training itself as how our machine learning works on real seismic and real wells.
Indeed, this is a unique way of integrating synthetic and real data set in training stage itself. Jyoti, during this entire process, do we do any validation as well?
Yes, Ayan, absolutely. Following the training of our convolutional neural network on synthetic datasets, we leverage transfer learning to apply this knowledge to any well location. This enables us to conduct tests on real wells, evaluating the accuracy of property predictions, and assessing the alignment between the predicted and the measured properties. Furthermore, we provide a quantitative interpretation, assessing the quality of prediction in terms of correlation and normalized root mean square errors. This process allows us to gauge our confidence in the deep machine learning model even before applying that in a 3D context.
That the key to this workflow is the simulations we are doing using rock physics modeling. Or I can say the number of reservoir scenarios we are modeling. Then how do I decide how many scenarios are enough?
And you're right in your understanding. Indeed, the use of rock physics to model various reservoir scenarios is the key part of the workflow. And for deep machine learning models and their validation, the more high quality training data available, the better the model prediction. In this case, we would like to capture the entire heterogeneity we are expecting in subsurface as per our geological understanding. If I give you an example, let's say that we have a drilled well that has encountered 15% porosity in the reservoir interval. Then as we move away from the well location, what can happen to the porosity? It can be either more porous or tighter reservoir. However, the maximum porosity could only be the critical porosity. Hence, we can scenarios of tight porosity like 2% and maximum range would be the critical porosity. Similarly, as per our geological understanding, we can vary thickness of the reservoir, saturation of the reservoir, and quality of the sand. The idea is we would not like to train on scenarios that don't exist because this would make our model perform more poorly. Additionally, we do not wish to skew the results by over-representing certain scenarios in the training. That is, we would like the distribution of porosity values in the real data and training data to be in the similar geological range.
Thank you, Jyoti. Also, I would like to know in terms of number of wells, how many synthetic wells should be created at a minimum? Is there a way to find out the sensitivity of this parameter?
We should create at least 100 synthetic wells. Let's say for our 200 millisecond synthetic with 2 millisecond sampling, this results in about 10,000 training images, which is adequate to train the CNN. More synthetic wells or a longer time window increases the number of images in the training and hence accuracy. Ideally, as I mentioned in the previous question as well, that we should try to capture the range of possible logical scenarios in the area that is being analyzed.
I see. Another question which came to my mind, Jyoti, when you say hundreds of synthetic wells, do we have a physical location of these wells in our field? If so, how are we placing the synthetic wells in field? And if not, then why?
No, Ayan, we don't have any physical locations of synthetic wells in our field. It is a pseudo data set created for the CNN training. Hence, there is no location assigned to these wells. It's only the signature of these wells in terms of reservoir properties, elastic properties, and later the AVO behavior in synthetic gather, which matters to us, and this is what we will use in CNN training. You're right in your understanding that the AVO behavior of these synthetic wells may match to the real seismic AVO gather somewhere in the field, but we don't know where the match is. In fact, there is no need for us to know where that signature matches. Till the time we have the modeled AVO response to various reservoir scenarios, I believe that's sufficient for us to proceed with the CNN training.
Jyoti, I understand that overfitting is a common problem in deep learning. I wonder if overfitting also applies in case of CNN.
Absolutely, Ayan. Overfitting is possible with any form of supervised learning. It is important to compare the training and validation misfit as a function of epochs. The number of epochs is a hyperparameter that defines the number of times the network will iterate through the entire training dataset. The number of epochs is a hyperparameter that defines the number of times that the network will iterate through the entire training dataset. The number of epochs act as a regularization parameter, which is quite similar to pre-whitening in deconvolution or inversion. Increasing the number of epochs improve the fit to the training dataset, but at the risk of overfitting. This is why it is important to choose the maximum number of epochs in conjunction with the validation data. In addition, the CNN employs other regularization strategies such as dropout. Also, like I was mentioning before, that increasing the number of unique images reduces the risk of overtraining, and that is why we put so much effort into creating a big data set to train the CNN, and that's why WellGen, the module where we are creating the synthetic catalog, is very important.
Thank you, Jyoti, for clarifying this. In terms of application, as you said that we can simultaneously predict multiple properties using one CNN model. Now, from your experience, which properties would you suggest predicting using this approach?
And although that's a very subjective question, however, it will depend upon the project's goal. But if I look in terms of the realm of reservoir characterization, I would prioritize predicting reservoir properties like porosity, saturation, or volumetric. And in addition, we recommend predicting elastic properties like acoustic impedance, shear impedance, and density. It is worth mentioning that the CNNs in Hampson-Russell software can also be applied for classification type studies, meaning that you can predict specific probability of a specific lithology or the probability of a most likely class. For example, probability of sand, shale or shaly sand, or the probability of gas, water, or oil.
Thank you, Jyoti, for sharing this. One last question, which is about the application of this technology. Where do you see the application of rock physics-driven machine learning? Is it in exploration stage or development stage of a field life cycle?
And you see, the technology can be applied to both exploration as well as development field. For example, in exploration, where we have limited well control, using rock physics model to generate various scenarios of the reservoir will help significantly to predict better subsurface models using deep learning compared to what we have been doing conventionally. In development case, we will have better control for validation. The reservoir properties estimated from rock physics guided machine learning can be used with more confidence. Although I must say that we have more sophisticated technologies to apply for reservoir characterization when we have a good distribution of drilled wells in the area. But if I compare the advantage of application, then indeed this technology solves the basic limitation of machine learning in exploration field. Another value in the production type setting is the fact that we are predicting multiple reservoir properties with one training model, leading to significant time saving in delivering the results.
Thank you very much, Jyoti, for sharing your thoughts. It was indeed a very informative and insightful podcast series where we discussed the basics of machine learning, deep learning, and the challenges in using deep learning in the realm of reservoir characterization. So theoretically, we talk about rock physics and how it has been integrated in the workflow to generate a synthetic catalog, thereby overcoming the data limitation challenge for applying deep learning. And lastly, we saw how convolutional neural networks are used in Hansen-Russell to derive multiple reservoir properties simultaneously. And to our listeners, we appreciate your time tuning to our podcast channel. If you have any further questions or topics you'd like us to cover in future seasons, feel free to reach out. Until then, keep rocking and keep exploring.